Hello, I'm Tony Lentz with FCT Assembly, and I'm here to talk to you about water-soluble solder paste. Is it wet behind the ears or the wave of the future? FCT Assembly set out to develop a new lead-free water-soluble solder paste because water-soluble technology has fallen behind no-clean technology. Most of our competitors and we have focused on creating new and improved no-clean solder pastes because that is the direction many of the high-volume users are going towards. But water-soluble solder paste is still used largely for high reliability applications which require removal of the flux. And it's certainly true that water-soluble flux residues are much easier to remove than no-clean fluxes. Is a new solder paste wet behind the ears? This poor gentleman would agree that wet behind the ears is the general state of affairs. But we do a lot of performance testing in our lab to help incubate the product to get it ready for use out in the real world. Here's the general process that we use when we formulate a new solder paste. First, we set performance objectives for the paste. We want to have very clear goals on what we want that paste to do. Then we develop multiple formulations, and we start producing small batches of the formulations to run testing. The tests that we choose to run are designed to measure the performance in different aspects of the solder paste. And in a lot of cases, we're actually creating new test methods in order to evaluate some process or some aspect of the paste that we can't directly measure, let's say. Then we compare the results of testing on new pastes to well-known current products. And then we continue to repeat this process until we meet the objectives that we set. Here's a general description of most of the ingredients that are used in solder paste fluxes. First, you have solvents. These are liquids, usually organic solvents with relatively high boiling points. They dissolve the other ingredients to make a uniform mixture. Then you've got rosins and resins. These add some body or some thickness to the product and also lend some activity to the product. Next, we have activators. Activators are very important to the function of any soldering flux. The activators will remove oxides from the solder powder and the surfaces to be soldered, and they help and promote soldering and wetting. Without activators, fluxes simply would not work. Surfactants are also used in some cases to aid in wetting or flow of the solder paste, and then also it helps to improve cleaning of the flux residues. Then we also use what's called rheology modifiers. That enables the solder paste to behave like a liquid when it's under pressure and like a solid when it's not under pressure, so it enables it to be printed. And then there's other trade secret ingredients which we would call gray magic. Of course, I can't talk in much detail about those without disclosing the actual formulations. Here are the performance attributes that we were looking for in this new lead-free water-soluble solder paste. First, we wanted it to be environmentally stable over a range of operating conditions. Our customers use solder pastes in high humidity environments, low humidity environments. Sometimes the temperature in the process area can get quite warm, especially inside of printers. So we wanted to make sure this solder paste is very stable over a wide range of those types of conditions. We want flux residues that are easy to wash off. Sometimes we use ingredients in solder pastes, water-soluble pastes, that are not truly water-soluble, but we use other ingredients such as surfactants to help make those non-soluble ingredients washable. We want the solder paste to have a long stencil life. We want it to be able to be printed and have pauses in printing and to last at least over an 8-hour workday on the stencil. And we also want the print characteristics to be very good. We want the volumes to be uniform and the standard deviation of printed solder paste volume to be low. We want the reflow characteristics to be excellent. We want wetting to be nominal. We want very low solder balling and very low graping. Here are the test methods that we use to evaluate all of these performance characteristics. First, we do environmental stability tests. These are 3 standard tests that we use. Mass change with air exposure in both high and low humidity. Basically, we take a dish of solder paste open to the air, store it in a low humidity environment and a high humidity environment, and we measure the mass change over time. In high humidity, water-soluble solder pastes tend to gain mass pretty rapidly because they absorb moisture out of the air. In low humidity environments, there's very little gain of mass due to water absorption, but there can still be oxidation of the powder occurring, and evaporations of solvents can occur out of the solder paste, which might result in actually a mass loss in some cases. Tack force change is measured with air exposure and humidity. So over time, water-soluble solder pastes tend to lose their tack fairly quickly. We want to measure how long the tack actually lasts in both high and low humidity environments. And then the last test that we do is called a 6-hour mix test. So that's basically where we throw roughly a kilo of solder paste into a kitchen type mixer, turn it on, and let it run for 6 hours open to the air. So that's aggressively shear thinning the solder paste and also oxidizing the solder powder. So if a paste is not balanced in terms of activators and powder protectants and things, then it's quite possible that in that 6-hour mix test the solder paste will thicken up and it can actually become Play-Doh like in consistency and stick to the mixing blade in extreme cases. In terms of print tests, we do two different types of print tests. Typically we do an 8-hour stencil life test that has pauses in it. And then we also do a print speed variation test. We want to see how our solder paste print over a range of different print speeds. Typically with our smaller lab printer we run 20, 50, and 100 millimeters per second, which covers the print speeds that most of our customers would use in the field. In terms of reflow tests, we have a reflow test board that we use. We can measure wetting or spread of the solder paste on both ENIG and OSP surface finishes. And then we also measure solder balling and graping with that same test board. Washability, we do two different types of tests. We take reflowed circuit boards and we wash them off under the tap, sort of low flow water, so worst case wash scenario. And we make sure that all the residues come off the circuit board. And then we also take a look at the flux residues themselves, and just a quick test is see how soluble they actually are. Do they make clear solutions in water or are they cloudy? In this evaluation we tested 3 different types of solder paste. We changed the names to solder paste A, solder paste B, and new solder paste. They were all made with SAC 305 Type 3 solder powder. Here are the results for the environmental stability test of mass change in open air. So this is a 24-hour test. Paste is in a dish open to the air. We have 2 different humidity conditions, 20% and 55%. The 20% is represented by the gray bars. The 55% humidity condition is the blue bar. And then the mass change in percentage by weight is here on the y-axis. So the 3 solder pastes we tested, A, B, and new, are shown here. You can see at 20% the mass changes are quite low. Solder paste A lost a little bit of mass. Solder paste B lost a little more mass. It dried out a little bit. The new solder paste actually gained a little bit of mass. But mass change less than 0.1% by weight, indicated by the red dashed line, is generally what we use as a measure of good stability. Now in terms of 55% relative humidity, all 3 of these solder pastes gained way more than 0.10% by weight of moisture out of the air. So what we're looking for here is we're comparing the performance of these 3 pastes against each other. Solder paste A had moderate performance at about 0.25% by weight mass gain. Solder paste B was the highest at about 0.40% mass gain. And then our new solder paste fell in between those two at about 0.31% mass gain. We wanted to be sure that the new solder paste performed at least as well as the other 2, and it's in between the performance of these other 2 solder pastes that we tested. Here's the environmental stability results for tack force. So we did 2 different types of tests here. On the left we have a graph of tack force plotted over a 3-day time period. So we stored tack force coupons in a humidity chamber at 55% relative humidity and then measured the force once a day for 3 days. On the right we have tack force over 8 hours, which is more common working life for solder pastes. Most people aren't going to use solder paste out open in the air for more than an 8-hour time period. So looking at the tack force change over 3 days, you can see paste A is the blue line. It drops after the first day, drops again after the second day, and then it kind of levels off. So it reaches a minimum tack force between 60 and 70 grams force based on the Japanese test method. Solder paste B drops off significantly after 24 and 48 hours and reaches a minimum of just over 20, but it starts out at 80. So you can see it loses quite a bit of tack force over this time period. And then the new solder paste was not so good performance compared to the other two in this particular test. It actually lost the most tack force over 24-hour time period, and then it just dropped down to near zero after 3 days. The new solder paste did not perform well, and I would not recommend using it over 24-hour time period open to the air, which, like I said, is very uncommon. Most people are going to run within this 8-hour time window on the right. So in this particular case, you can say solder paste A is the blue line again, loses a little bit of tack force after 1 hour, then it holds its tack force throughout the rest of the 8-hour time period. Solder paste A is one of our most stable water-soluble solder paste, and this is why we make that claim. Solder paste B drops off in tack force to level off pretty close to what solder paste A values are giving us, but then it continues to drop throughout the 8-hour window. Solder paste B, we normally recommend do not use it longer than 4 hours on the stencil because of this drop in tack force. The new solder paste in this test, however, first of all starts off with a higher tack force, and then it drops a little bit, but it levels off. So within an 8-hour workday, it holds its tack pretty well, at least equal to the performance of the other two solder pastes. So that's what we were looking for out of this new solder paste. Here's our final environmental stability test, which is what we call a 6-hour mix test. This is about a jar or two of solder paste put into a kitchen type mixer and mixed open to the air for 6 hours continuously. There's aggressive shear thinning going on, and there's also air oxidation of the solder powder occurring, and then that reacts with the activators in the flux, which can sometimes have a thickening effect on the solder paste. So what we do to measure the change in the solder paste in this test is we measure viscosity initial, and then we measure a final viscosity after the test is complete. This final viscosity is actually measured after the paste restabilizes overnight inside of a jar. Then we look at the viscosity change. So in this case, solder paste A had an increase in viscosity of about 8%. That tells us that solder paste A is not very stable in this particular test, that it's reacting as we mix air into it. That's not desirable. Normally what we would expect to see is a decrease in viscosity. So the new solder paste has showed us a 9.2% decrease in viscosity, which is a good result. Viscosity should decrease in this test because of the aggressive shear thinning that's taking place. So anything less than 10% indicates good stability, and that's what our new solder paste gave us in this test. This is our stencil life and response to pause test on the printer. The solder pastes are printed through a stencil that has some BGA arrays with 10 mil rounded square apertures. It's a 5 mil thick stencil, so the area ratio is about 0.50, which is a really small area ratio to be printing type 3 solder paste through. So that gives us a very aggressive test and fairly low transfer efficiency numbers, as you can see here. And then what we do is we print 2 circuit boards and measure solder paste volumes. Then the paste sits idle on the printer for 1 hour. Then we print 2 more boards and measure volume. Then there's another idle time of an hour. Print 2 boards again and measure volumes. Then we wait 2 hours. We repeat that, wait 4 more hours, and then we print the final 2 boards and measure volumes at the 8-hour time mark. So here we have the chart of transfer efficiency on the y-axis versus the time on the printer on the x. So over this 8-hour response to pause test, solder paste A, the blue bar, is very stable. It starts out at about 42% transfer efficiency, and then it levels off right around 40 through the duration of the test. So solder paste A responds well to the stencil life and pauses on the stencil. Solder paste B is the red bar here. The red bar, it does not perform as well as the other 2 solder pastes. Solder paste B starts off with a higher transfer efficiency at about 45%, but then it drops off aggressively at 2 hours and at 4 hours, and then drops again at 8 hours. So solder paste B is drying out on the stencil and not releasing as well as the other 2 pastes after these pauses. The new solder paste is the green line. New solder paste is very stable again in this test. It starts off in the upper 30s, and then it holds its performance over the 8-hour timeline in this test. So solder paste A and the new solder paste perform very well. Solder paste B not quite as good as those other two. So the new solder paste is doing what we expect it to do and performing equal to or better than our other two solder paste in this particular test. Here's the print characteristics of our solder paste at the 3 different print speeds that we use. So we ran it at 20, 50, and 100 print speeds, which are represented by the red, the yellow, and the green bars for each paste. And then again, we measure transfer efficiency through that same BGA array, 0.50 area ratio. And what we're looking for here is we want these print volumes to be roughly equal. So for solder paste A, all 3 of these print speeds are pretty much equal. So it responds and prints very well at the whole range of print speeds. Solder paste B, however, prints very well at 20 and 50, but then at 100 millimeters per second, it dropped off in volume. So it's not quite rolling and responding as well at that higher speed. The new solder paste did something similar. The volumes were very equal at 20 and 50, and then they dropped off again at 100 millimeters per second. So that just means that we wouldn't recommend customers use it at 100 millimeters per second, or just in general, once you get up to those higher print speeds, you can expect a little bit lower volume out of the solder paste. It's not necessarily a bad thing, it's just something that we want to know so we can accurately describe how to use our products to our customers. These are some representative images of printed brick definition of 2 of these solder pastes at 50 millimeters per second print speed. This is a capture off of our SPI system. Solder paste B, you can see these bricks are not very uniform. There's some peaks and some smaller bricks here. The new solder paste is much more uniform in terms of brick definition. So it's not all about volumes necessarily, but brick definition and uniformity is important. So our new solder paste definitely gives nice uniform bricks at a moderate print speed. Alright, let's switch gears and talk about reflow testing for the solder pastes. This is an image of our reflow test board that we use internally for R&D. It has several different types of patterns on it. At the top here in the middle, that's a wetting or spread pattern. Below that, there is a pullback pattern which we use to measure solder balling. There are QFNs on this that can be used for void measurement, although I didn't do any of that in this particular paper. And then we have these graping test patterns here. There's 4 of these, and you can actually put a numerical measurement on graping performance of the solder paste. In terms of a reflow profile, this is the profile that we used to test all 3 of these pastes. Length is about 4 to 4.5 minutes, 45 C to peak. That's pretty typical for the profiles that we set up. The ramp rate's about 1 to 1.5 degrees C per second. Time above liquidus was 60 seconds nominal with a range of 50 to 70. And then the peak temp is 245 C nominal with a range of about 240 to 250 C. Here's a close-up of the wetting test pattern and how it works on our test board. So what we have here are a series of parallel lines. There's 12 of those. There's 15 solder paste bricks printed on each line, and the pitch changes from 0.1 millimeter in the center out to 0.4 millimeter on the outside edge. So after reflow, the solder paste wets in the center and starts to spread down the line, and it spreads farther and farther. And if ideal wetting is shown here, for ENIG, this would be ideal wetting, 100% spread. The lines are completely covered with solder. This is relatively poor wetting on ENIG. This would be a 76% measurement. OSP, on the other hand, gives overall much lower wetting than ENIG does. OSP, poor wetting on OSP would look like this, where most of the bricks didn't even spread down to meet each other. And so that's about 7% wetting. And then good wetting on OSP would look like this. This is about 36% wetting. So those are the types of numbers we would normally expect or a range of performance of wetting on this test pattern. Here's the wetting that we actually got for our 3 solder pastes. The ENIG wetting is shown by these golden bars. OSP wetting is shown by the dark red bars. Solder paste A, B, and the new solder paste are on the y-axis, and the wetting or spread percentage shown on this x-axis. So in all 3 cases, the ENIG wetting is almost ideal. It's near 100% for all 3 of these solder pastes, as it should be. Enig's fairly easy to wet by solder paste, and it works very well. OSP, on the other hand, is much more challenging, so OSP wetting measurements can be used to differentiate between these three pastes. So paste A has a wetting percentage of about 23%, which is also pictured over here to the right. That's one of the patterns from one of the paste A boards. Paste B was lower than that at about 17% wetting. You can see what that looks like. And then the new solder paste was higher than both of those at 25%. So the new solder paste wets and spreads as well as or better than the other two solder pastes. Here are close-ups of the solder balling and graping patterns and how we use those to measure performance. So the solder balling pattern has a series of dots that are roughly 20 mil diameter, and they are different distances apart because we use different types of overprint on these. So the overprint ranges from 500% here to 1250% down here. So we're aggressively overprinting on the mask, big time overprint. Then after reflow, the paste pulls back into a central ball, and then there's some solder balls left in the flux ring. You can see here, like right here, up here. So what we do is we inspect the pools of flux for solder balls, and we count what's the largest percentage overprint that has less than 10 solder balls and the largest percentage overprint that has less than 5 solder balls. And that gives us a rating on solder balling performance. And then in terms of graping, here's what the graping pattern looks like. So the graping pattern has 4 columns. There are solder mass defined and non-solder mass defined rounds and squares. And the area ratio of the apertures ranges from 0.60 for the 12 mil aperture down to a 0.35 area ratio for the 7 mil aperture. It's a 5 mil thick stencil. So very aggressive area ratios, like very difficult to print. So in general, graping occurs as your deposits get smaller. So as you start printing through these small 8 mil, 7 mil apertures with these 0.40 and 0.35 area ratios, at such a small solder paste deposit, it lends itself to create graping. And this is what the paste looks like after reflow. So then what we do is we look for the number of deposits that show graping, like this one here. And then we count up the total number of deposits that have graping out of 4 of these patterns, and then we calculate a graping percentage. Here are the results of the reflow testing for graping and solder balling for our 3 solder pastes. We have solder paste A here, solder paste B in this column, and the new solder paste in this column. And then on the very right is the best possible result, or the goal, the ideal performance. So in terms of graping percentage, solder paste A is relatively high in graping, about 42%. Solder paste B is about 9% graping, it's very low. The new solder paste is just a little higher than solder paste B, about 17% graping. Best possible graping would be 0 in this case. Solder balling, the biggest pattern that had less than 10 balls. Solder paste A, 900% overprint. Both B and the new solder paste had the largest possible, 1250% overprint for less than 10 balls. And then solder balling less than 5 balls, solder paste A had 750% overprint as the largest pattern. Solder paste B, 1100%. And then the new solder paste, 1250% overprint, had less than 5 solder balls. So again, that's the ideal result. So in terms of comparing these 3, the new solder paste was excellent on graping, just about as good as solder paste B, which is very low graping. And it was better than the other 2 in terms of solder balling. Let's switch gears and talk about water washability. So here's images of 3 of the circuit boards after wash. You can see paste A looks pretty clean, but there is some slight residue in between these. Solder paste B, again, fairly clean, but you can see just a tiny haze between these solder joints. The new solder paste, to me, looks a little bit cleaner, although all 3 of these images are very similar to each other. We took the rinse water that we used to wash these boards and we captured it in beakers so you could see how soluble the solder paste fluxes are. So solder paste A is very cloudy. Solder paste A is not very water soluble. It forms a cloudy mixture. Solder paste B and the new solder paste are much more clear mixtures in water, and that means that they are more soluble in water, therefore they're easier to wash off. So we're at the end of all the test data, Now I've put together here is a table that summarizes all the results from all these tests. And I wanted to come up with a good way of comparing and contrasting these three solder pastes and give them sort of a score against each other. So what I did is I listed out each test that was run in these rows here. And then I have the solder pastes in these columns, solder paste A, B, and the new solder paste. And I gave each paste a ranking. So each paste got a rank. So if they were equal in performance, they all got 0 rankings. If one of them was in the middle, like on this next test, high relative humidity, environmental stability, new solder paste was middle in performance. Solder paste B was worse, so it got a minus. Solder paste A was better, it got a plus. So if performance was clearly better of one of the pastes, it gets a green plus. If performance was clearly worse of that solder paste in that test, it gets a yellow minus. So as I went down through all of these, what I did is at the very bottom I summed up the rankings, all the pluses and minuses. So solder paste A had a total of 5 green pluses and 3 yellow minuses. Solder paste B was 2 and 6, and the new solder paste was 5 and 1. So compared against each other, the total rankings, if you cancel out positives and negatives, so the total ranking for solder paste A is 2 plus. Solder paste B gave us a total ranking of 4 minus, and the new solder paste gave us a total ranking of 4 plus. So 4 plus is the best overall ranking out of all three of these solder pastes with this set of test methods. So when you're in this particular case, we were able to create a solder paste that was better performance overall than our other two solder paste products. So in conclusion, our development process did create a new high-performance lead-free water-soluble solder paste. The new solder paste exceeds the performance of 2 existing solder pastes that have been on the market for many years. And the test methods that we use are quite challenging. We're always generating new test methods to actually make solder paste fail so we can find out where their limits are. And then this new solder paste, we might say that it's wet behind the ears because it's new to the market, but it does promise to become the wave of the future of our product line. I would like to thank the R&D team at FCT Assembly, especially my counterpart Eric Sletton, for his work running tests and gathering data for this paper. That sums up our presentation on a new water-soluble solder paste. Thank you for your attention. I appreciate your time. If you have any questions, please email or contact us at the email address or the phone number shown here. Again, thank you and have a great day. Bye-bye.